Hi, welcome to the Shiko Math Practice Lab. Remember, learning through practicing. And in this video, we're going to practice some problems to the related rate problems here. So this is the related rate practice number 1. So it's kind of like the level 1 related rate problem. It's kind of like simple problems. You just need to set up the equations and then it's kind of the simple level, the related rate. Then in our next practice set, we're going to take a look at a little bit of advanced related rate, and it's more like a word problems and see how do we set it up here. So in this level 1 problems here, we're going to take a look at 7 problems, in this practice here. Okay, so let's go ahead and let's start. Okay, all right, so the first ones here, so like I said, let's take a look. We're going to take a look at like the 7 problems. So this is the first 5. And then we're going to take a look at these other 2. So total 7 problems. So we're going to do the level 1. Like I mentioned before, the level 1 related rate are pretty simple and it's pretty straightforward. Okay, so let's go ahead and start. Okay, so the first thing here, so we talk about this is the, the A is the area of the circle with radius r, and the circle expanded the time as the time passed. Find the dA dt in terms of the dr dt. So like during the lecture, we know the related rate. So what do we need to do? First, we set it up, and then we kind of find a relation for the variables. So this one is pretty straightforward. We want the A is the area and the radius is r. So it's kind of like kind of straightforward. So we know the area, we learned this when we were pretty young. The area is pi r squares, right? So we know the area and the radius, they're going to change when the time passes here. So that's why here, in order to find the relations, right? So I would say, take the derivative with respect to, okay, so this is what we call this respect to t, respect to the variable t's, right? So when the a, you take the derivative, this will be the dA dt, and then you take the derivative to the r is a function, so I use the power rule, so this is 2 pi r, then the dr dt is here. That's it. It's pretty easy, right? So the things here, of course, we need to know what is the meaning. So this is what? This is, we say, is the area change of t, right? When the t passes. And this is what? This is the radius change, right? When the t passes, how fast the radius changes, right? So this is the radius rate of the change. How fast the radius change. This is the area rate of the changes here. So the first problem is pretty simple. Like I said, the level 1 practice is a very simple related rate problem. Okay, so now let's take a look at the second one here. The second one is say, suppose the oil spills from a ruptured tank and spread a circular pattern here. The radius of the oil increases in a constant rate of 1 liter per second. How fast is the area of the spill increasing when the radius is 30 meters? So like we, when doing the lecture, we say the things here, let's try to write what we are looking for, right? So let's write, so what is it? 1 meter per second. This is dr dt, right? That's the radius change. This is the 1 meter per second here. Then we are looking for is the areas changes, right? So how fast the area change? This is what we are looking for here. What is here, when increases the radius is 30 meter, that means this number r is equal to 30, right? So remember, that's what during the lecture we thought about, you write it out, each value, what they represent. Then the hardest problem in the related rate is to try to put the two variables together. So now this one is not bad. This is the area and the radius. So I know area is equal to the pi r what? Pi r squares, right? Now you want to find the area changes. So you take the derivative of both sides to the t. So it's dA dt. Just like we did problem number 1, this is 2 pi r dr dt here, right? Now we are looking for the dA dt. So we just plug in the value. We know the r is what? It's 30. And how fast is dr dt? Is 1, right? So I know this one will give me 60 pi meter square per second, right? Because the area is meter square. So this one's here is pretty easy. Like we mentioned before, the hardest part for the related rate is to find those equation. And this is the equation kind of connect your, kind of put your variables together here. Okay, now let's take a look at the other one. Number 3 is here. We say a cylindrical tank. So it's a kind of the cylinder with a radius of 5 meters being filled with water. All right. Oops, what is that? Okay. So now let's see here. This is, oops, that's not a good picture. Okay. My eraser or something. What is the, okay, so let's see what happened to my, okay, now the eraser work. Aha, good. Okay, so that means I have a cylinder tank here. All right, so this is my cylinder. Okay, so this is my cylinder tank. And let's say the cylinder tank has a radius here. This is 5 meters, right? So let's see, let's try to write it out, all those numbers and what we want to find is here. Okay, so they tell the cylinder's tank R is 5 meters. And because this is a cylinder, so I know R is a constant, right? So it's defined all the way. It's being filled water at a rate 3 meter cube. So what is that? So because here's a meter cube, so I know this is a talk about volumes, right? So let's say that the volumes, the dt. So how fast the volume of the dt is 3 meters cube per minute here. Now we want to find how fast is the height. So here, this is the height, right? So what we are looking for is dh what? dt here. So we are looking for this one. So in here, we have 3 variables. We have v, r, h, correct? v, r, h. Like I said, the hardest one is try to find the relation of those variables. This one is not too bad. We know how to find the volume of cylinders, right? So how to find the volume of the cylinder? So the volume is equal to what? You find the pi r square, you find the circle area, each circle area, and then times what? Times the height, correct? Okay, good. And now we are looking for the dv dt. Remember here, the r is what? R is a constant, right? R is not going to change here. Okay, so the dv dt is here. So the dv dt, so which variable I'm working on? See here, I'm working on is the h and v. R is a constant, correct? Okay, so now dv dt, this will be equal to the pi r square dh dt, correct? So I'm looking for dha dt. So now I can plug in all the value I have. This is 3 is equal to pi r squared. So pi to the r squared is 5 to the square dh dt. Okay, so I can simplify. This will become pretty easy, right? So dh dt is just equal to the 25 pi over 3. All right, so this is what? So the meter per minute, right? Because of the height, right? So that's why I know when you try to pour in the water, then my height going to increase. So in the rate of the height change is 3/25 pi meter per minute here. So this one is pretty easy also. Okay, so now let's take a look at the next problem, number 4. So the number 4 tell you the radius of the sphere is increased at a rate of 4 millimeter per second. How fast is the volume increase when the diameter is 50 millimeters here? Okay, so let's see how many words we have. We have the radius is increased for the 4 millimeter. How fast we want to find the volume increase, right? Okay, so now how fast the volume increases. So the dv dt. This is what we are looking for, right? So what is a 4 mm, 4 millimeters second? So this is radius is increased. So this number so is dr dt. And so what is the dr dt here is 4 millimeter per second. And then in here, they throw something there. They say a diameter is 50 millimeter. So I know the variables here have r's, right? So what is the diameter? If a diameter is 80 millimeters, that means r is what? R is 40, correct? So now let's see here, we have the variable v and r. And now, what is the relation for the sphere, the volume for the sphere? This one we know also. Volume is equal to what? 4/3 pi r, how many? Cube, that's right? Okay, so now we want to find the dv dt. So this one would be pretty easy. So you just say the dv dt is equal to 3. So this is 4/3 times 3. Then you use the power rule, the r square. So you have 4 pi r. I'm sorry, I forgot something. Yes. When I take the derivative of r, don't forget the dr dt, right? So now I have a 4 pi r square dr dt. Now let's substitute the values, right? So 4 pi r square, r is what? R is 40. So r is 4. Okay, so r squares, right? R is 40 millimeter square. And the dr dt is what? The dr dt is 4, right? So now I know, so this one will be, so this will be 25600 pi, and then this is an m millimeter cube per second, right? Because it's a volume here. So this one is pretty straightforward as well. Okay, we are going to get a little harder, especially the second part, but right now those are the very kind of the simple problem. We need to know how to do that. Okay, so in here, number 5 here, they tell you, they said that the area of a triangle with the sides of the length A and B and the contained angle theta is 1/2 AB sine theta. Wow, this is pretty nice. They already tell you the formulas, right? So now let's say in here I have A equal to 2, B equal to 3 centimeter, And the C is increase at a rate, it's 0.2 radian per minute. How fast is the area increase? All right. Okay, so now let's try to, like we did before, write it down. What are we looking for? So this is our formula. So A is equal to 2, B equal to 3. Those are what? Those are the constant. Okay, then they say theta increase at the rate 0.2 radian per minute. So what is this one? This is d theta dt is 0.2, right? And now I'm looking for, so what I'm looking for, the area increase, right? So area increase. So that's what I'm looking for. I am looking for dA dt, right? So this is what we're looking for. Then when theta equal to pi over 3, so theta equal to pi over 3. So what is my variables here? So I have A and theta, right? So now, like I would say, the hardest one is to find a relation. Here it's pretty nice. It's already give you the relation. So this is what we call it, we learned this in the pre-cal, how to find the area of the triangle if you know the two sides. So this will be 1/2 AB sine theta. Okay, now take the derivative. Okay, so now let's take the derivative of both sides here. So I will have a dA dt, correct? dA dt is equal to the 1/2 AB because AB are constant. Now sine, what is the derivative of the sine? The derivative of the sine is the cosine theta, right? Then don't forget the d theta dt. Now we want to find the dA dt, so I just substituted the value we have. So it's 1/2. What is A? A is 2. What is B? B is 3. What is the cosine? What is the theta? It's pi over 3. And what is the d theta dt? Is 0.2. Okay, so now let's see that here's a, you can cancel that. The cosine pi over 3, I think it's 1/2, right? Okay, so now this will give you, so the cosine pi over 3, so this is 3/2 times 0.2. Okay, 3/2 times 0.2, it will give you, so I think it will give you 0.3 meters, 3.3 meters square by what is the times here? Minutes here, right? Okay, so let's go. Okay, so here we have, so that's what is here. We have 0.3 centimeter. Okay, so it's a centimeter square per seconds here. Okay, that's it. Okay, let's take a look at the last two. The last two's here. So let's see here the number. So it's suppose 4x squared plus 9y equal to 36. Let's try to find the given part. So here, the first part here, so they want to find the dx dt's, right? So here they said 4x squared plus 9y squared equal to 36. So I will take the what? I will take the derivative, both sides. So I have an ax, don't forget dx, what? dt plus 18y, because both of them related to the t is dy dt. So what happened to the 36? The 36 is zeros, right? So I'm looking for the dx dt, so I can have ax dx dt is equal to moving the y over 18 dy dt. So the dx dt is just equal to ax negative 18 negative 18y dy dt. Now let's try to plug in the value, x equal to 2, so this is 16. Negative 18 times y, what is y is here? Is 2 the square roots of the 3. Oh no, not the square roots. Okay. So 2 over 3. So this is 2 over 3 square roots of the 5. What is dy dt is 1/3, right? Okay, so that if you simplify this, this will give you negative square roots of the 5 over 4. So that means the dx, so this is dx dt is decreasing, right? Because it's negative. Okay, so the same way, let's take a look at the dy dt. So this is 4x squared plus 9y squared equal to 36. Okay, same old, take the derivative on both sides. So this is ax dx dt, right? Don't forget, plus 18 dy dt. And is equal to what? Is equal to 0. So what I'm going to find the dy dt, okay, so this is 18y, don't forget. So this is 18y dy dt is equal to the negative ax dx dt, correct? Then you divide by 18y, divided by 18y. So the dy dt is going to be 18y negative ax dx dt. Dx dt is what? Is 3. Now I can substitute the value negative a. What is x here? X is negative 2 times 3, 18. What is the y here? And here, oh, okay, here I don't. Okay, so the y here, okay, I already did that. So, okay, y here is what? Is 2 of 3. Why I always like to put the square roots. That's weird. Okay, so let's try to erase it. Good. All right, so the y is 2 over 3 square roots of the 5. Okay, so if we simplify this and we will get a 4 over square roots of the 5, okay? So this one is pretty mechanical, right? So you just when you take the derivative of x and the y, don't forget you are taking derivative with respect to t. So you always need to have a d. That's what in here you always have dx dt, dy dt, dx dt, dy dt. They solve each other. Okay, now let's take a look at our last ones here. The last ones here will tell you 2 cars starting from the same point. One travels south at 60 minutes per hour, and the other travel west at 25 minutes per hour. And what rate the distance between the car increased 2 hours later? All right, so we have another word here, right? Let's try to, so this is travel 60 miles, and that is travel 25 miles. And how much the distance increased 2 hours later. So we're looking for is what is the distance increased, right? Okay, like we did in the lecture, we say let's always do our pictures, right? So we say I have 2 cars. We start at the same place. Then one go here, okay? That's a little too big. Let's, okay, so one go to the west, then one go to the what? One go to the south, right? So here, this is west, this is south. So I can say that here, this is x, this y. And then they want to find the distance. So what is the distance? That means here, this is the distance, right? So this is the distance. I would say, well, let's call this is D. And because one travel west, one travel south, so we know this is right triangles, right? Okay. Now let's try to put it together, right? So we said the dx dt, right? Okay, so the variables here, we have the dx dt. So what is the dx dt here is 60s, right? Then the dy dt. How fast we travel? 25. Okay. And then I have a variable x, I have a variable y, and I have a variable d. So I'm looking for the distance increases, right? And after 2 hours here, okay? So we are looking for dd dt, right? So this is what we're looking for. Okay, so just like we talked before, we say, okay, now let's try to put all this together. D here is the Pythagorean theorem. So this one is not bad. So you say D is equal to the square roots of x squared plus what? Plus y squared, correct? Okay, so now I will simplify this a little bit. I can say this is x squared plus y squared to the 1/2. So I'm going to find the dt. So I say, okay, let's take the derivative of both sides. Okay, so here this is dt. Okay, so when I take the derivative, so this is 1/2. So what I need to do, power rules, right? So this is 1/2, and then this is x squared plus y squared negative 1/2, right? And then what other rules I need to use here? I need to do something inside here. What is that rule? Yes, we call the chain rules, right? So the chain rules here, though this is 2x. What is the x? I need to have a dx dt. And plus 2y dy dt. Okay, so now we can start to put the value in here. So this is the 1/2. This is a negative 1/2, really just become to the denominators, right? Okay, so now let's take a look at the xy. In here, I don't have xy's here. But then we say, okay, we have one more condition we did not use. It's 2 hours. Okay, so think about it. If x is travel 60 miles per hour, so what is the x value will be after 2 hours? How many miles? 100 what? 120, correct? Okay. Then the same time, we say y is 25 miles per hour. So after 20, what is here? It's 50 miles. Okay. So now we have all the values. That's great. So let's put it inside here. So x squared. So it's 120 square plus 50 square. Correct? Okay. And now the top here is 2x, it's 2 times 120, okay? And well, in fact, I don't need to use the 2. I can simplify it and make it, I can simplify it. So why to simplify it? This 2, you can factor the 2 out and cancel with this 2. So I don't need to double, write it repeatedly. Okay, then I have x is 120. Now dx dt, what is here? 60, right? Then plus y is 50 times dy dt is what? Is 25. Okay, so I made the calculations. So here nicely the inside the square roots come out 130, and this is 8450. So that means this is 65 and then the miles per hour. Okay, so that's why I know the distance between this car here and this car, the distance between these two cars, they are increasing like 65 miles per hour here, right? At the 2 hours timestamps there. So how fast the distance become further apart is 65 miles per hour. Okay, that's it. You know, we did like the 7 pretty simple level 1 type of the related rate problems. Even they are simple, but they are kind of important, right? Because they tell you the basic concept, how to set it up. Then in our next video, we're going to look at the level 2 related rate problems. The problems is still just like the setup. We need to like maybe, find a, be careful about the setup and then check on the relation, the variables, the constant to see which one is which. Then like we said, maybe, how to find the best relation, what is the relations here between those variables. That's most likely is the hardest part for the, for the related rate problem. All right, that's it. And nice talk to you and looking forward to talk to you in our next practice. So we're going to do a little bit more advanced related rate problem. Okay, you have a good day and I'll talk to you later. Okay, bye.